In this video, we will present Supergroup 2's schema matching and mapping exercise and solution. Our supergroup consists of groups 3, 5, and 8, and our resulting company is called G2 Cinema and Rental. To develop our solution, we followed a standard procedure. First, we analyzed the MySQL data sources we were tasked with integrating, that is, an online DVD rental company database and 2 cinema operator databases. After this, all representatives of each company met to discuss their respective databases. And through such a roundtable discussion, we identified semantic matches. We found that some tables occurred in all databases, some in only 2, and others were unique to each database. We then transferred our identified matches into mappings. To do so, we discussed each match and decided on the best mappings that we all agreed on. Whilst doing this, our goal here was to minimize data and information loss while still adhering to original business requirements. We decided on this goal as we assumed that in the merging of the 3 businesses, it would be beneficial for them all to be able to run as they have done historically, at least in the short term anyway. Other important decisions at this stage included deciding on attribute and table names, where semantic matches were identified, and also agreeing on a standardized naming convention. After this process, we were able to create our mediated schema, first drawing it as an ERM diagram and later undertaking the physical implementation. From there, we could implement our mappings to build transformations and jobs in Pentaho, with special attention given to ensure error handling was adequately performed. And finally, our Pentaho job could be executed to perform the physical integration. As previously described, our initial situation involved analyzing 3 data sources. The first, for an online DVD rental company called No Name, for which the entity relationship model was shown here. The second was for the cinema operator 5 Star. And the third for cinema operator FLW. When analyzing the 3 databases for semantic matches, we found 3 cases of matches. Case 1 was where information existed in one database with no match to information in the other databases. An example of this is the movie content table in the online DVD rental database. This table is used to store what content each copy of a movie includes, for example, a bonus disc. Our second case was where a match was found across 2 of the 3 databases. An example of this is the sitting and presentation tables in the cinema operator databases. They are named differently and we'll deal with this later, however they describe the same information and hence we regard them as a match. Another second case example was the modeling of movie genres. Again, both cinema operators included genre information. One, however, modeled genre as a table that could be joined to their movie table, while the other modeled it as an attribute within their movie table. For a physical implementation, the first approach is technically better as it is normalized to BCNF and therefore will avoid repeated data entries. So we therefore decided we would stick with this approach. Our last case, case 3, was where a semantic match could be identified across all 3 databases. This only occurred once for each database's movie table. This was a pretty easy match to identify as our tables were all named the same. However, within each table contained different attributes, which meant we had to decide on a common set of attributes to include in the mediated schema. Our resulting mediated schema looks like this. You'll notice our unique movie content table in place as before with no changes. Our presentation table included, which will encompass all of the data from the sitting table as well. The genre table, which will take on the genre attributes of each movie from 5 Star's database. And the integrated movie database, which will combine all 3 databases' movie information. After some considerable work, we built all Pentaho transformations. The final executable job is presented here. As you can see, it involves a number of transformations executed in a linear fashion. Many of these are simple transformations. For example, information about the directors of movies were only stored in one of the 3 databases, and hence the directed transformation simply takes directed data from one input only and checks for existing entries before writing into the mediated schema. I will now pass to Jonas, who will perform a live demo of our Pentaho job.
Welcome to a short live demo of our data transformations. We start this demonstration by having a look at our three source databases. As you can see, every one of them is filled with some example data. In contrast to this, our media database is currently empty and has no data in it. Now we switch into Pentaho and start executing the main transformation job. All necessary transformations are included in the right order, coupled with some supporting jobs, like checking database connections and the existence of the necessary tables and columns. Because it is the first time the job gets executed on this database, the existence check for the required columns for saving the old primary keys fails, and the job has to create these columns in order to be able to correctly map foreign keys. After the job has finished, all the data from the source databases will be transformed and saved according to our mediated schema. Switching back to our database view, our mediated schema is filled with the data from our source databases. Now the mediated database is ready to receive queries and provide results with the combined data of all three databases. That's it for this short live demonstration. I hope you got an overview of our transformations, and with this I will hand it back to Luis.
In building our Pentaho transformations, we encountered three challenging and interesting problems. The first was creating transformations that would ensure our resultant database would not contain duplicate data, a likely occurrence if the job is executed for a second time, for example. As a solution to this problem, we included a process in our transformations that checks for already existing entries when data is inserted into the mediated schema. If an existing entry does not exist, the new entry is flagged as new and written to the mediated schema. The second challenge we encountered was that of foreign key updates. Given we are combining data from different sources into integrated tables in many cases, we realized primary keys for each data entry would have to be redefined. Redefining primary keys itself is not a problem. However, in doing this, foreign keys from data entries in related tables would also have to be changed. To perform such a process, we created a transformation that added 3 columns to every table in the mediated schema. Each column represented a temporary primary key from each respective data source. This meant that for each data entry we had 2 primary keys, the original primary key from the data source and the new primary key in the mediated schema. With this in place, we could perform a join on the foreign key and original primary key to identify the relationship, and then rename that foreign key to be aligned with the new primary key. The final major challenge we faced was ensuring that there were no typos in our data entries from different sources that were intended to have the same meaning. We discussed this issue and decided that this would most likely occur for customer names, genre names, and movie titles. To solve this problem, we built a transformation that conducted a fuzzy string search over the customer name, genre name, and movie title attributes in the mediated schema. We used the Jarrow-Winkler algorithm instead of the Levenstein algorithm, as it allowed us to specify a value between 0 and 1 to indicate the decision point at which two strings would be deemed the same. For example, we specified 0.8 or 80%, which meant that if the JW algorithm's results specified a match of greater than 80%, we would consider these to have the same meaning. After a match was found, the transformation specifies that a full outer join be conducted to join the matched and unmatched results with no duplicates. To show you evidence of our functioning integrated database, we have prepared a few example queries. In the first, we are selecting all columns from the movies table in the mediated schema and ordering by movie title. You can see the query returns the table's integrated data entries and all its columns, most notably the movies that all 3 companies had previously stored in their databases. In the next query, we select the number of tickets sold to each customer. In doing so, we are selecting from the customers, tickets, and movie table and grouping by movie title and customer name. The results are presented below the query. Interestingly though, not all ticket sales are shown, as only one of the cinema operators included customer details. For our final example query, we count the number of times a movie has been shown in one of our cinema halls, and again the results are presented below the query. That concludes this video. We hope you have gained some valuable insight into our integration. Thanks for watching.